Okay, I'm going to start the recording here. So now, class, we move into section 6.6, which deals with applications to physics and engineering. So you're going to learn here. Let me just turn off my email here. I don't want any distractions. Okay, good. So how many have to take a physics class or an engineering class? Okay, let me see here. There's a number of you: Masume, Helen, Mark, Opiemi, Clea, IB, Shalom. Yes, so calculus, of course, is involved in these courses, and that's IB, of course. That's that's one reason why calculus is often a prerequisite for these types of classes. And we're going to learn some fundamental applications where calculus is used to help us, like in physics. And what I'd like to do is just give you a little guided tour of the book here. We'll look at maybe the first three examples. And so let's proceed here. Let's proceed. So, okay. Let me see though. Hold on. Oh yeah, no. This is what I want. This is what I want. Right. So, okay. The term work is used in everyday language. This is section 6.6. It's used in everyday language to mean the total amount of effort required to perform a task. In physics, it has a technical meaning that depends on the idea of a force. Okay, so force is a push or pull on an object. Okay, if you push a book across a table, or Earth's gravity on a ball, that's a push or a pull. So if an object moves along a straight line with a certain position function, then the force on the object is defined by Newton's second law of motion. So Newton's second law of motion is force equals mass times acceleration. How many have heard of that? Newton's second law of motion. Okay, Opiemi and Helen and IB and Mark. Right, a number of you. And so, of course, position of the object is S is a function of t. So position S of the object is a function of t. The derivative of position, ds dt, is equal to velocity. And then the second derivative of position S is equal to acceleration. And that's what you see here in the gray box. So how many remember S stands for position of the object? Maybe from Calculus 1. Okay, Opiemi remembers that, Masume and Mark, good. And I teach Calculus 1, and certainly that's covered. So let's let's just move forward here and talk about, I want to ease you into this chapter, because I know not everybody's had physics. So let's talk about units. So in the metric system, mass is measured in kilograms. Displacement's measured in meters. Time is in seconds, and the force is in newtons. So Newton is equal to a kilogram times meters over seconds squared. That's the units for newtons. How many have heard of a newton before? Okay, Masume and IB and Avery, wonderful, and Mark, Opiemi, wonderful, wonderful. So now in the US system, the fundamental unit of force is pounds. Okay, so pounds is a unit of force. Mandy, I can bring that up. I can bring that up, or you could look at that on your own too. But at the end of class, I'll mention that. Okay. So, all right. You're welcome. All right. So let's proceed on a little bit here. Okay. So here's something that hopefully you should have seen, maybe in high school or even middle school. How many know that work equals force times distance? Okay, Clea remembers that, and IB, and so in order, and Helen, in order for you to do work on an object, you have to move the object a certain distance. So straight work is equal to the force applied to the object times the distance. Okay, so, and again, we look at the units. If force is measured in newtons and d distance is in meters, then the unit for work is the Newton meter, also called the joule. Okay, the joule. However, if force is measured in pounds and distance in feet, then the unit for work is called the foot pound. Okay, so two different units of work. And they have a couple of nice little illustrative examples here. So if you, for instance, hold on here, if you lift a 1.2 kilogram book off the floor to put it on a desk that's 0.7 meters high, the force you exert is equal and opposite to that exerted by gravity. So force is equal to m times g. G stands for acceleration due to gravity, okay, which is 9.8 meters per second squared. So this is why, and maybe I can just make that a little bigger there. Yeah. How many have seen 9.8 meters per second squared, acceleration due to gravity? Okay. Jonathan and Clea. And all right, so that's certainly something you'll see. You're seeing it now. And once you compute the force, then the work done is just equal. It's just equal. Hold on here, one moment. No, Clea, we use 9.8 here. We don't round that 9.8 to 10. That's a good. Maybe maybe in. I mean, boy, that your high school physics teacher did that. Wow, Jonathan, that's kind of amazing there. I'm surprised about that. But here we'll use 9.8. We want to get the right answer, So, okay, well, so work then is equal to force times distance. So we take 11.6 newtons times 0.7, 0.7 meters, and we get 8.2 joules. Okay. So, all right. Well, let's proceed on then. Hopefully, this is all pretty straightforward. If we talk about now in terms of force being in pounds and distance being in feet, if you take a 20-pound weight and lift it 6 feet, the pounds is already a unit of force. So that means then that the work is equal to 20 pounds times 6 feet. That's 120 foot-pounds. So these problems are very nice for when you have a constant force. But what we can do in calculus is we can deal with a force that is not constant. So let me show you what I mean here. Okay, so I'm going to draw an X and a Y-axis here. And I'm going to have it starting, I'm going to have an A. Hold on. I'm going to have an A and a B. And actually, yeah, that's fine. That's fine. And then I'll have some function here. And this function, f of x, is my force function. Okay, this is a force function. That's fine. And you can see it differs. It differs because now your force is a function of position. Okay, so like for instance, the force at position x1 equals this value, but at a different position x2, the force equals this value, whatever that is. So you see now with calculus, we're allowing a force to be variable. And you see what we can do is we can say, okay, well, I want to compute and I want to say this the right way. So x1 and x2 are different positions. So when the object is at position x, okay, which is like say x1 feet from the origin, the force equals this value. Okay, let me just put this up here. This is f of x1. And when the object is at position x2, the force applied on the object is f of x2. So the force is lessening in this case. Well, the object goes from A to B. Okay. So work was done on the object in moving it from A to B. The question is, what is the work? Well, we have to find a way to compute work where our force function varies with respect to the position that the object's at. Okay, and that's a big concept here in section 6.6. So if we go back to the book here, this is all in the recording. If we go back to the book, what we could do, and they have it, I want to keep the highlight here. So again, they're saying, let's suppose the object moves along the x-axis in the positive direction from x equals A to x equals B, and at each point x between A and B, a force acts on the object, where f is a continuous function. You just saw that in the whiteboard. We can divide the interval from A to B into n subintervals, each subinterval having equal width. Okay, and then we can choose a sample point in each subinterval and compute the force at that point. Okay, if n is small, then if n is large, I should say, if you take a lot of subintervals, then delta x is small. And since our function is continuous, the values of the force function don't change much over the subinterval. Okay, so in other words, if I wanted to compute the work in moving, I have it here. If I want to compute the work, let me just kind of, let's say I want to compute the work in moving the particle from x sub I minus 1 to x sub I, which means move it along the length of that subinterval. Then work is force times distance. Okay, and now they have a little typo here. Instead of a capital F in the book, in the e-book, they have I'm sorry, instead of a lowercase f, they have a capital F. That f should be a lowercase f in that highlighted gray box. But the work done in moving the particle along that one little subinterval is approximately equal to the force on the subinterval times delta x. And to get the force, we pick a position, like a value, in that subinterval. But since the subinterval is so small, basically the force is constant on that subinterval. So the work along that subinterval and moving the particle along that subinterval is equal to the force over that subinterval times delta x. Delta x is the distance that the object moves on the subinterval. Okay, that's just a little distance. That's the length of your subinterval. Work is force times distance. So if you wanted to find the total, if you wanted to approximate the total work, you would just compute the work along every subinterval, the work that it takes to move the particle along each subinterval, and add up all those work values. And you'll get what you see there in Formula 3. Okay, are there any questions so far? All right, well, naturally, if we take more and more subintervals, if we let n go to infinity, our approximation for the true work value is going to get better and better. If we let n go to infinity, what's this Riemann sum going to become? If we take more and more subintervals, make them smaller and smaller.
An integral.
That's right, Shalom. It's going to be an integral. Excellent. That's right, Yonatan. It's going to be an integral. Very good. So, okay. Well, so now then, we have a way to compute the work. This would be the work done in moving an object from A to B. And now, because you know calculus, you're able to allow your force function to vary with respect to position x. Okay, are there any questions on that? Okay, well, let's proceed on to some examples here. Let's proceed on to some examples. So, example 1. Okay, and let me just hold on here. Just want to remove some of the highlight here. We don't need that all there. Okay, so in this problem, they want you to, they say when a particle is located at a distance x feet from the origin, a force of x squared plus 2 pounds acts on it, acts on the particle. How much work is done in moving the particle from x equals 1 to x equals 3? So you're moving it 2 feet, right? X equals 1 to x equals 3. Well, the work is just the integral of your force function with limits 1 to 3. So you end up getting then 50/3, and 50/3 is just 16 2/3 foot-pounds. So that's the work done. Are there any questions on that? All right, who's feeling good so far? Give me a thumbs up if you're feeling good. Okay, Yonatan's good, Clay is good, wonderful. Daniel's good, excellent. And Susanna's good, excellent, excellent. Okay, well, let's proceed on to the next example then. So, Hooke's law. What is Hooke's law? Hooke's law is a law from physics, and it states that the force required to maintain a spring stretched x units beyond its natural length is proportional to x. Okay, so I always think of, like, for this kind of example, I think, and K is, by the way, a spring constant. K is dependent on what spring you're using. But, let's say you have I like to think of a rubber band, Okay, how many have taken a rubber band and stretched the rubber band? Okay. And do you notice that if the rubber band, the more you stretch it, you notice how it wants to, like you have to apply more force to stretch it more? Do you notice that? Clea notices that. Sure. I mean, it's once you really pull that rubber band, really stretch it, it's wanting to go back into its natural length. So you see, you have to apply greater force. So the force is proportional to the distance x that you are stretching the rubber band beyond its natural length. That's an example of Hooke's law. I want to be a little careful. Hooke's law, I mean, they're talking about springs. I think I'm using rubber bands because, you know, rubber bands is something we've all, I think, worked with, right? So, okay. So, and then in the figure here, here's Hooke's law. You know, you have the natural position of a spring where the spring's neither stretched nor contracted. And then when you stretch the spring, the force is equal to K times X. The more X is, the greater the force is needed to stretch the spring. So in this example, and let me see here. Give me one moment here. I want to just kind of remove a few things here. Okay, so in this example, work needed to stretch a spring. So a force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to a length of 15 centimeters. How much work is done in stretching the spring? Well, so you're stretching the spring a distance of 3 centimeters, okay? According to Hooke's law, the force required to hold the spring stretched x meters beyond its natural length is equal to K times X. When the spring stretched from 10 centimeters to 15 centimeters, and maybe I'll highlight this, when the spring is stretched from 10 centimeters to 15 centimeters, the amount stretched is equal to 5 centimeters. Okay, so in other words, you're starting out with the spring being stretched 5 centimeters or 0.05 meters. We have to change centimeters to meters because you know, we need to keep our units correct. So F of 0.05 equals 40. Are there any questions on that so far? Clea? Yep.
So why do we change to meters since all of the units in the problem are on centimeters?
Well, they're being a little tricky there. The newtons, units of, like newtons is the metric unit of force, and you have to have your distances in meters. So you're going to have problems where, you know, why don't they just give us meters in the first place? They don't tend to do that. I mean, sometimes they might, but we tend to think, you know, maybe centimeters is better for this application, you know, for measurement purposes. But then we got to remember when we work the problem out to convert centimeters to meters. So it's all so that's why we have to do that. Like newtons goes with meters, but it's no problem to convert centimeters to meters. So 5 centimeters equals 0.05 meters. Good question, good question. And you know what we have to do is we have to determine that spring constant K. Yes, Susanna, question?
Yes. Well, where did the 40 come from?
Oh, it's told in the example there, below example 2, it says that a force of 40 newtons is needed to hold the spring. So that F of X equals 40.
I see it. Okay.
All right, good question.
Thank you.
Good question. Sure. And Mark, you had a question? That's right. Mark says, yep, Mark's saying exactly right. Very good. Very good. So we need to find the spring constant K. So what I'm going to do is well, I know that 0.05 times K is equal to 40 because 40 newtons is required to hold the spring stretched a distance of 0.05 meters. So based on that then, right, based on that, we can determine that K is equal to 800. I know it doesn't come out here in the ebook, but K is 40 divided by 0.05, and that's 800. And so now we're able to find the work done in stretching the spring. We're able to find that work. Okay, the work here, it's highlighted right here. It's the integral from 0.05 to 0.08 of 800x dx. So it's the integral of the force function. The force function is, we found that K is 800. The force function then is 800 times x. So the work then is the integral from going of 800x dx, where your limits are 0.05 to 0.08. Because we start out with the spring stretched 0.05 meters or 15 centimeters, and then it's stretching it to 18 centimeters, which is 0.08 meters from 0.08 meters away from its natural length. The natural length was 10 centimeters, so 15 centimeters is 0.05 meters stretched beyond 10 centimeters, and 18 centimeters is 0.08 meters stretched beyond 10 centimeters. And so we work it out and get 1.56 joules. Are there any questions on the second example? Okay, let's do this third one here. Let's try to get this one in. Yes, Jonathan, question? You're good?
Sorry, I was muted.
Okay.
How is 18 centimeters 0.08 meters? Shouldn't it be 0.18 meters?
Well, you see what they're doing is in the problem, it's a good question. The natural length of the spring is 10 centimeters. So you're starting out with the spring being
So it's
stretched.
18 minus 10 is the change.
Right. 18 minus 10
Oh,
and then 15 minus 10, exactly. All right, great, good question, good question. Okay, let's get this last one in here. Okay, work needed to lift a cable. So in this problem, okay, a 200-pound cable is 100 feet long and hangs vertically from the top of a tall building. How much work is required to lift the cable to the top of the building? Okay, and they mention here in the solution, we don't have a formula for the force function, but nevertheless, we can compute the work. So what they do here is, so this 200-pound cable, it's 100 feet long and it hangs from the building. How much work is required to lift the cable to the top of the building? So here's a picture of the building. Here's a picture of the building. So normally the x-axis is horizontal, but they're just, they want to keep the variable x. So it's a vertical axis. The cable goes, it's 100 feet long. So you're looking from 0 to 100 feet on the x-axis. And what you can do, you see, is you can look at some point on the x-axis, and then there's a delta x there. So let me just clarify what that means. Okay, so I might go a few minutes over. Stay if you can. It'll be in the recording, but I think it'll benefit you if I get this covered here. I love the questions that are being asked today. A lot of good questions. So I'm going to draw this cable, okay? I'm going to draw this cable. This won't take long. The cable the cable is 100 feet. And this here is the top of the building. And what I'm going to do is I'm going to pick two chunks of cable. This is the first chunk of cable. This is the second chunk of cable. Each cable is delta X feet wide. And we want to consider, okay, that the second chunk of cable is further down than the first chunk of cable. Both key pieces of cable, okay, have the same length, and so they weigh the same, right? If we want to know how much, how much does delta X feet of cable weigh? Delta X feet of cable weighs, okay, well, the cable weighs 2 pounds per 1 foot, because you see there's a 200-pound cable. It's 100 feet long, so that means the cable weighs 2 pounds per foot. If we multiply that by delta X feet, you notice that the feet cancel, the feet simplify out, and what you're left with here is 2 delta X pounds. Okay. So again, delta X here is the width. It's the width of that piece of the piece of cable. It's the width. And both pieces of cable have the same width. And and since the cable weighs 2 pounds per foot, each piece of cable there, cable 1, the piece of cable 1 and piece of cable 2 weigh 2 delta X pounds. Now my question is, which is going to take more work? To bring up the cable 1 to the top of the building, or to bring up the first piece of cable to the top of the building, or to bring up the second piece of cable to the top of the building? Jonathan right away says the second piece of cable. Why is that, Jonathan? Why would that be? Well, they both weigh the same. Both pieces of cable weigh the same. But the second piece of cable is more distance. Hold on, somebody said more distance. That's right, Victoria. The second piece of cable here is further down. So you see, what we can do is we can think of this 100 feet of cable. We can think about dividing it up into a bunch of little pieces of cable. And then we can compute the work needed to bring up each piece of cable. Each piece of cable is going to require a different amount of work, because each piece of cable is a different distance from the top of the building. Okay, hold that thought, Shulam. Hold that thought. So you see, whether we bringing up the entire cable to the top of the building is the same as cutting up the cable in a bunch of little pieces and bringing up all those little pieces to the top of the building. Okay, so now if we go back to the book, and we're almost done here. I appreciate your staying a few extra minutes. The work needed to bring the ith piece of cable up to the top of the building is the force, which is 2 times delta X pounds, times the distance, which is xi feet. Okay, so that's 2 delta x times xi. Now what we want to do is we want to add up all the little separate pieces of work, okay, to get the total work. So the total work, okay, would be the sum of all the pieces of work, the 2xi times delta x. That's the work to bring up the ith piece of cable to the top. We add up that sum, we let n go to infinity. That means we take that cable and subdivide it into smaller intervals. The approximation gets better and better. It becomes an integral, and we end up with 10,000 foot-pounds. Okay, are there any questions on that? That's example 3. But how many think offhand this is really pretty fascinating, this kind of idea? All right, Yonatan's liking it, and Susanna likes it. Yeah, we're gonna do some amazing things in section 6.6. All right. On that note, let me stop the recording. Okay. Are there any questions? We're good?
Thank you, Professor. Have a good day.